Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. 2014 question 8 on probability, a tree diagram, very important. Especially this question because we can associate it to COVID, seen as it's the year of COVID. Blood tests are sometimes used to indicate if a person has a particular disease. Sometimes such tests gives an incorrect result, either indicating a person has the disease when they do not. So has the disease when they do not, and we're calling that a false positive, or indicating they do have the disease, they do not have the disease when they do, and that's called a false negative. It is estimated that 0.3% of a large population have a particular disease. A test developed to detect the disease gives a false positive in 4% of the tests and a false negative in 1% of the test. A person picked at random is tested for the disease. It takes a little bit of time to just wrap your head around false positives and false negatives, okay? So just keep coming back to what I've highlighted in green and orange when you need to figure it out, okay? So a tree diagram starts from the left and you work your way over. So you pick a random person and you're wondering, do they have the disease or do they not? Okay, and in all cases, probability adds up to 1, in that out of this here, out the branches out of the tree give you all the different possible scenarios. So this is quite yes/no type scenario. They either have the disease or they don't. So 3% are believed to have the disease, so or 0.3%. 0.3 as a decimal is 0.003. Okay, and then if you subtract that from 1, so 1 minus 0.003, I don't trust myself with that amount of zeros. So on my calculator, I'm after doing that, and I get 0.997. So 99.7% of people then do not have the disease. Okay, and you can see they add up to 1. Okay, so then you come to these, I would say, the nodes of your tree. Okay, so from the people that have the disease, did they test positive or did they test negative? Okay, so we have a value filled in here which is test negative. Okay, 0.01, which is 1%. So this is this piece of information here, which is a false negative. Now, if I come up here to see what is a false negative again, they do not have the disease. So the test says they do not have the disease when actually they do, because everybody here has the disease. So the test is saying they don't. Okay, so if 0.01 of them are here, again, you go 1 minus 0.01 and you get 0.99 of them. So 99% of people who have the disease tests positive. Okay, let's come down the bottom. So let's have a look at this branch of people, the people who do not have the disease. Okay, so we would expect very few of these. If you do not have the disease, we'd expect very few of them to test positive. We'd expect the majority of them, if they do not have the disease, to test negative. Okay, so these are what we call the false positives. It's a person who where the test says they have the disease when actually they don't. Okay, so false positive was 4% of the cases. So change 4% to a decimal and you get 0.04. Okay, so therefore down here 0.96 or 96% of them will test negative. Okay, So that's that. And then to work out the overall probability of something happening, you follow the branches. So there's your random person. What's the probability that they have the disease and test positive? Okay. And the value goes in here. And what you do is you multiply the probabilities along the way to give you the overall probability. So it's 0.003 multiplied by 0.99 to give you quite a small value, 2.97 by 10 to the minus 3 is what my calculator is coming back as. What does that mean but with an everyday number? Well, that's scientific notation. So that minus 3 means that decimal point moves 3 places to the left. Okay, so 1, 2, 3. So I'm getting 0.00297 for that one. Okay, to convert it to, I suppose, normal decimal notation. There's nothing wrong with putting it in as a fraction if it lets you 297 over what's that, 100,000. That's okay. There's nothing wrong with you putting in scientific notation. That's also okay. So it's whatever format suits you. Okay, so I'll write it out here. I'm getting 297 over, I think that's 100,000. 1, 2, 3, 4, 5. And if I S to D him there, it's 2.97 by 10 to the minus 3. Okay, they're all the same, different ways of writing the same number. Okay, so how many then people have the disease and test negative? So this is going to be even smaller. And I am getting for this one 3 over 100,000, okay? Or if I S to D him, I'm getting 3 by 10 to the minus 5, okay? So the decimal point is here. So 1, 2, 3, 4, 5 frog jumps back, and everywhere there's a jump without a number, you put in your zeros. So 0.1, 2, 3, 4, and the 3. Okay, right, down to the next one. How many people do not have the disease but test positive? So you would hope that this is also a small number. And I am getting 997 over 25,000, not as small as I'd like. And okay, so they don't write this in scientific notation because they reckon the number is big enough that they don't have to. So 0.03988. Okay, now this is the one you'd expect to be big. You would hope that most of the population does not have the disease and tests negative. Okay, so it's 0.997 multiplied by 0.96. And I am getting for that one 2991 over 3125 S to D him 0.95712. Okay, and I don't round at this early stage because there's so many places of decimal. You'd end up getting the likes of 0 for that if you rounded too much. Okay, so that's why I don't round. Either leave them as the fractions if you wish, or whichever way you want. Okay, so that's that tree diagram. Make sure you're okay with it. Let me know if you need any more of it explained or whatever. All right, so then what type of questions do they ask? Hence or otherwise, calculate the probability that a person selected at random from the population tests positive for the disease. Okay, where a tree diagram comes out on its own then is in the analysis of what's happening. So it's really, I suppose, easy to answer a question like this once you have the tree diagram done. If you tried to answer this question, given this data without a tree diagram, you would do really well to be able to answer it. Okay, so hence or otherwise, calculate the probability selected at random tests positive. Okay, so there's test positive and there's test positive. Okay, it doesn't say anything about whether they have the disease or not. It just says calculate the probability that they test positive. So these people test positive and these people test positive, okay? So we're happy with this ones or this ones. They all test positive. So we end up adding those probabilities together because they all meet the criteria of testing positive. 0.03988. Okay, so 0.3988 plus 0.02297. So I'm getting I forgot a 0. It looked a little bit high. Okay, let me just put that in again. An extra 0 up there that I forgot. 0.00297. It just looked a little bit high. 0.03988. Oh yeah, I see where I'm gone wrong. Sorry now.
Is there one less 2, is it?
Is it? Thank you, Aoife. Yeah, that's exactly it. So 0.002. So I had it a 0 instead of a 2. Now. Okay, cool. Thank you. Okay, so let's try adding them again now. 0.00297 plus 0.03988. Let's try it now. 0.04285 is what I did get when I was trying it earlier. 0.04285. Okay, so that is the probability. So if I convert that, so in my head, I just convert them to a percentage because I suppose the number makes more sense rather than decimal. So 4.285% of the population is testing positive for the disease. Okay, a person tests positive for the disease. What is the probability that the person actually has the disease? Okay, so actually has the disease. Give your answer correct to 3 decimal places. Okay, so what they're asking here is conditional probability. So what is the probability that they have the disease given that they test positive? Okay, so the probability that they have the disease, so it's DISCASE, intersecting with test positive over the probability that they test positive. So let me just explain that. So conditional probability is always on the top, the intersection between the two conditions over the second one. Okay, that's how I remember the formula. I'm just going to rub off the scientific notation if that's okay, to give us a bit of space, and I'll just come up here and do it. There's not much left, so there's no point going on to a different place. So what is the probability that they have the disease intersecting with they test positive? So it's this 0.00297 on the top, and then on the bottom, the probability that they test positive, okay, which is test positive and test positive, just in case you haven't the piece before it worked out. Okay, so what did we get for that? 0.04285. And let's put that into the calculator. 0.00297 over 0.04285. And I am getting 0.693 for that. Okay, which in percentages is 6.9%. Right. Okay. So what does that mean? A person tests positive for the disease. What is the probability that the person actually has the disease? Give your answer correct to 3 significant figures. Okay. 693. Okay. So that's not a great test. Yeah.
Is that who doesn't have it? Or?
That is, yeah. So that's why I was just checking. Did they ask you? Do they want you to I suppose interpret that result afterwards? So what does that mean? That means of all the people who test positive, how many of them actually have the disease? So we're getting just 7%. So that's not a very good test. Okay, and it comes down to all of these false positives that are coming. 4% of false positives is huge. Okay, so remember what a false positive is. It's the test is telling them that they have the disease even when they don't. Okay, so you can see some of the critical, I suppose, the life-ending diseases. If you had a test that told you you had a disease when you didn't, that test is just not viable in the medical world. Okay, so the next part there said the health authority is considering using a test on the general population with the view to the treatment on the disease. Based on your results, do you think that the above test would be an effective way to do it? Give a reason for your answer. Well, I would say that that test is not viable or shouldn't be used. Why? Because the person only has the disease 7% of the time, even when they test positive. Okay, so out of all that tests positive, only 7% have the disease. Okay. Part B then. So part B is statistics. So a generic drug used to treat a particular condition has a success rate of 51%. A company is developing 2 new drugs, A and B, to treat the condition. You can see this is very much along the lines of COVID. They carried out clinical trials on 2 groups of 500 patients suffering from the condition. The results show that drug A was successful in the case of 296 patients. The company claims that drug A is more successful in treating the condition than the generic drug. Use a hypothesis test at the 5% level of significance to decide whether there's sufficient evidence to justify the company's claim. State the null hypothesis and state your conclusion clearly. Okay, there's going to be a lot of this going on over the next few months as we watch different companies bringing out different drugs to combat COVID. Okay, I think Pfizer are the first ones that look like they're going to be on the market. Their testing looks like it's good. So chances are they will bring out a vaccine. It'll be quickly followed by other companies who are also developing trials, and they will claim or they will make a hypothesis that their vaccine is better than the Pfizer one. Okay, so are they allowed to make such claims? Well, no, not unless it's backed up by data. Okay, so they have to do some statistical analysis to see, on average, is their drug better than the other one? And that's what we call a hypothesis test. So for a company to come out, and say that theirs is better, they have to have data behind that, otherwise they're going to get sued. Okay, so how does it work? Well, you state what's called a null hypothesis, and you state what's called an alternate hypothesis. The null hypothesis, as we called it, adopts the status quo. In other words, everything is equal, everyone is happy, there are no differences. Okay, so the null hypothesis in this would be that drug A is the same as the generic drug. Okay, so that's the alternative. Sorry, that's what we call the null hypothesis. The alternate one is it's a bit like a revelation. So this is big news if the null hypothesis is true, which would be drug A is better than the generic drug. Okay, so when hypothesis test questions are generally being marked, you generally get a third of the marks for just stating these. You then get a third of the marks for the analysis, and then a third of the marks for writing a conclusion. Okay, so the analysis then, well, they've done some testing, they selected a group of 500, and they've figured out that 296 of them were successful after they used drug A. Okay, so therefore, I'll just change to blue for this part. The success rate of drug A is 296 over 500. And if I convert that to a decimal, it's 0.592. Okay, so a bit more than 50%. Okay, we put what we call a margin of error around that. In other words, because we didn't sample the entire population, we wonder, did we just get lucky in the 500 that we picked, in that 296 of them are good? Or I suppose, is that what we call representative of the entire population? Is it a good sample? Okay, so because we haven't tested anybody, we put, it's a bit like a tolerance around our data, and that's called the margin of error. So the margin of error is very much related to N, which is the amount of people that you sample. Okay, so in this question, your margin of error was 1 over root N, which is 1 over root 500, because that's how many people we sampled, and we got 0.045 for that. Okay, so what we do is we add it and subtract it to our sample that we took. Okay, so it'll be 0.5. Well, I'm going to need more space. Okay, so let me come up here and do it. So it'll be 0.592 minus the margin of error up to 0.592 plus 0.045. Okay, so 0.592 minus 0.045 is 0.547 is less than P is less than, and then add it on 0.637. Okay, so I'm just going to put a box around that. Okay, so what does that mean? So under it, I'm going to just write the percentages. P here normally stands for the entire population. Okay, once you add and subtract a margin of error to your sample data, it's felt that you have enough of a guard band around it to be what we call representative now of the entire population. So when I read this, I know that the population value is somewhere between 54.7 and 63.7%. Okay, and then it's in the context of the question. So the success rate of drug A is somewhere between 54.7% and 63.7%. Okay, so that's my data. Okay, then let's conclude. Okay, so what does all this mean? Okay, so come back up to the question again. the generic drug has a success rate of 51%. So what you do is then you compare its data with your data for drug A. Okay, and you can see that our drug A, even with us taking a chunk off for garbanding or taking off what we call a margin of error, it is still better than the 51%. Okay, so in fact, we can conclude that drug A is better than the generic drug of 51%. Okay, so how do we write it? Well, we say the success rate of the generic drug equal to 51% lies outside. I never said that was actually called a confidence interval when you set it up. The confidence interval established above. Therefore, the result is significant. We reject the null hypothesis and conclude that drug A is better than the generic drug. Okay, drug A is better than the generic drug. Okay, or another way of phrasing it is there is sufficient evidence that the new drug is better than the generic drug. Or however you want to phrase it, you will find teachers phrase this slightly different. It seems to change every couple of years as to what is the best way to phrase it. But in essence, the message is you compare the data, I suppose the standard data to your confidence interval. Does it lie within it or outside it? If it lies within it, you accept H0. If it lies outside it, you accept H1. Okay, so that's how you do what's called a hypothesis test. Okay. Right, part 2 then, the null hypothesis was accepted for drug B. Estimate the greatest number of patients in that trial who could have been successfully treated with drug B. Okay. Right, okay. So the best ones that could have been treated with drug B. Right, okay. The null hypothesis was accepted for drug B, okay? So drug B, we stated that drug B is the same as the generic drug, okay? So for the generic drug then, the margin of error would still be the same 500 patients, okay? Except instead of adding it on to 0.592, remember we got that from 296 over 500, we're adding it on to 0.51 minus 0.045 up to 0.51 plus 0.045. Okay, so you're adding your margin of error onto the data from the generic drug. Why? Because we said the null hypothesis was drug B, okay, which was drug B is the same as the generic drug. Okay, let's make some room. What you'll find then is your confidence interval, which is often called CI, is 0.51 minus 0.045. So I am getting 0.465. Less than P is less than 0.555. Okay, so estimate the greatest number of patients who could have been successful. Well, it was 55.5% of patients, basically. Okay, so out of the 500 that was tested, how many of them gives me a statistic of 0.555. So I'm kind of doing this, but what I'm doing is trying to figure out what was this number instead. So what was the greatest number in the trial who could have been successfully treated to give me 0.555. So multiply them together. And I'm getting 277.5. So you can't have half a person, so 277. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.